Hello everyone, I hope you're doing well. In this lecture, we're going to start by talking about alkene stability. So far we've talked about how to name alkenes, and there are different types of alkenes. You can have, for instance, an alkene with one substituent. So that would be called a monosubstituted alkene. And then you can have alkenes with two substituents. So those two substituents could be trans, so opposite each other. They could be cis, so they're on the same side, or they could both be on the same carbon. And these are called di-substituted alkenes. You can also have an alkene with three substituents, and there's really only one way to show that. And this is called a tri-substituted alkene. And then you can also have an alkene with four substituents. So that would be a tetra-substituted alkene. Okay, so now let's try to rank these in terms of their stability. So which of these alkenes do you think is the most stable? The monosubstituted, disubstituted, trisubstituted, or tetrasubstituted alkene? So I'll give you a hint. It has to do with hyperconjugation. So remember, hyperconjugation involves an overlap of orbitals, which will stabilize a bond or a positive charge, for instance. So which of these do you think has the most hyperconjugation? The tetrasubstituted alkene. So that is actually our most stable type of alkene. And again, that's due to hyperconjugation. The more substituents you have on the double bond, the more hyperconjugation there is, and the more stable it is. So that means that the monosubstituted alkene is the least stable alkene. Okay, so then let's talk about the cis and trans alkenes in particular. So again, we can have a trans alkene and a cis alkene. Which one is more stable? Well, let's think about this in terms of electron groups and VSEPR theory. So remember, in VSEPR theory, electron groups want to be as far away as possible from each other. So which one of these would satisfy VSEPR theory? The trans alkene, right? So trans alkenes are more stable because the electron groups are far, oops, I tried to combine two words together, are far apart. Oop, I did not leave myself enough room. All right, so let's just circle the trans alkene so we know that that is more stable. So even though disubstituted alkenes in general are more stable than monosubstituted alkenes, and then less stable than tri-substituted alkenes. Even within that category, we do have a variation in stability, and that has to do with the cis and trans alkenes. All right, so now how do we actually make an alkene? How can we perform a reaction to create a double bond? Well, that's where elimination reactions come in. So, in your textbook, if you have the 3rd edition, elimination reactions are covered in Chapter 7. If you have the 2nd edition of the textbook, elimination reactions are covered in Chapter 8. So just be aware that the chapters are slightly off if you have the 2nd edition. So let's talk about E2 reactions first. So let's see how an E2 reaction works. So I'm going to draw a substrate with a leaving group, and then I'm actually going to draw a base. So not a nucleophile, but a base. And we're going to say that this is a strong base for an E2 reaction. Now, what ends up happening in an E2 reaction is the base is going to take a hydrogen from a carbon that neighbors the carbon attached to the leaving group. Now, a simpler way to say that, because that's a little confusing, is to indicate the carbon using Greek letters. So the carbon that's attached to the leaving group is given an alpha designation, and then any carbons that are next to the alpha carbon are called beta carbons. So we have 2 beta carbons here. And then, like I said, the base is going to grab onto a hydrogen from one of those beta carbons. So one of the carbons next to the carbon bonded to the leaving group. So let's just make a little chart. So an alpha carbon is the carbon attached to the leaving group. A beta carbon is the carbon attached to the alpha carbon. All right, so now let's show that the base is going to take one of those hydrogens, and it could be any of the hydrogens on a beta carbon. At least in this case, we'll talk about other cases later on. And then the shared electrons will be left behind, and they'll form a pi bond. Now, when that happens, we'll technically create a Texas carbon down below. So the leaving group is going to leave in order to alleviate that strain on the carbon. All right, so 3 things all happened in the first step. So the base grabbed onto a proton, the shared electrons formed a double bond, and then the leaving group left. So we end up with our first product. So we have a double bond and then a methyl group attached to that double bond. So that is a monosubstituted alkene. We also have our conjugate acid because our base took a proton. And then we also have the leaving group, which is now negatively charged because it took electrons with it. So in this reaction, the rate determining step involves 2 reactants. So this is a second order reaction. So the rate law tells us that the rate of the reaction is equal to a rate constant times the concentration of the substrate times the concentration of the base. So this is kind of similar to how we categorize the substitution reactions, SN1 and SN2. The 1 and the 2, it depends on the rate of the reaction. So up above, the elimination reaction symbol E2 tells us that, again, we have an elimination reaction. So we're eliminating a bond. And then the 2 refers to the fact that this is a second order reaction. Okay. So now let's talk about another way to prepare alkenes, and that's an E1 reaction. So let's say we have the following substrate, and then we have a base, and this base is actually going to be a weak base. Now the reason that we don't need a strong base for an E1 reaction is that the leaving group is actually going to leave first. So this is kind of similar to an SN1 reaction, right? The leaving group leaves first. So we end up with a carbocation, similar to SN1. But again, this time we have a base. And I'll also put the leaving group there as well. So let's label our alpha carbon, so the carbon that was bonded to the leaving group, and then our beta carbons. So the alpha carbons in the middle, that was the carbon bonded to the leaving group. And then we have 3 beta carbons. And they're all equal carbons, they're all the same. So the base could take a hydrogen from any of those carbons. So let's just draw the possible hydrogens that the base could take. So it has 9 different, or yeah, 9, 9 different hydrogens that it could take. And we'll just show it taking, let's say, the one from the top here. And then that's going to create a double bond. And that's going to get rid of our positive charge on the central carbon. And the leaving group already left, so we don't have to worry about that. So for this reaction, we end up with a di-substituted alkene. We end up with our conjugate acid, and again, we have our leaving group. So in an E1 reaction, the rate determining step involves only one reactant. So this is a first order reaction. So the rate depends on the rate constant and then the concentration of just the substrate, not the base. So again, the symbol E1 tells us that we have an elimination reaction. So we got rid of a bond. And the 1 tells us that this is a first order reaction. Okay. So now we've learned about 2 new reactions. We already learned about substitution reactions, and now we know about elimination reactions. And we know that there's two ways to prepare an alkene, at least for now. We have the E2 reaction, where the base attacks first. So it has to be a strong base in order to attack right away. And then the leaving group leaves after a double bond forms. And then we also have an E1 reaction, where the leaving group leaves first, and then the weak base grabs a proton, and we form a double bond. So in the next lecture, we're going to go over some of the properties of substitution versus elimination reactions. So we'll talk about how temperature affects those reactions, and then we'll also talk about nucleophiles versus bases, because remember, in a substitution reaction, we use nucleophiles. But now we can see with elimination reactions, we use bases. So we'll talk a bit more about those different factors next time. I'll see you then.